As I indicated earlier, the next topic that I want to discuss with you is how do we reclaim soils which are outside of the desirable pH range. Of course, we have two pH conditions that need to be modified or amended. The first, as illustrated by the graphic that's in front of you now, is a soil which has a pH which is too high. We would call this an alkaline soil, and in some cases we may call it a sodic soil. Sodic, of course, comes from the chemical symbol or the chemical element sodium, and this is indicating that we have, for whatever reason, obtained a higher than normal sodium content in the soil. And since sodium is a cation and is found in the soil solution in appreciable quantities in these high pH soils, it is going to enter into the exchange reaction that we discussed earlier. That is to say that if we had a soil with a pH of 8.5 or above, we would be seeing a high percentage of sodium, chemical symbol Na, on these exchange sites. So this square box is representing a soil particle with its negative exchange sites. The Na, of course, is a sodium ion, and it's found on multiple numbers of these exchange sites. We would still have some other bases such as calcium there and or magnesium, and we would also have hydrogen. Even at a pH of 9, we would still see some hydrogen associated with these exchange complexes due to the fact that it has a very high adsorption affinity. The material of choice that we use for reclaiming or modifying the pH of these highly alkaline soils is the material gypsum. Gypsum, even though it's a hydrated salt, that means there's some water in the crystals, is basically calcium sulfate. So what I've shown here is that, let's say this is the condition of the colloids in the soil that are holding the exchange particle or the exchangeable cations. We apply gypsum, plus gypsum to the soil. Gypsum will go into solution in soil water and dissociate into calcium cations and sulfate anions. Now, once this takes place, we greatly increase the concentration of calcium cations in the soil solution. Because of this increased concentration, this allows the calcium to go on to many of these exchange sites, and since sodium has a very low adsorption affinity, it is likely going to be the first one that gets kicked off. So now after we've added the gypsum to the soil and we've got it in solution, I'm showing you a soil particle which now has exchange sites occupied by calcium, some hydrogen, and some other basic cations. Now, depending on the quantity of gypsum we apply, there could also still be some sodium on these exchange sites. But we would hope that we would, at least in the top foot or so, or 2 feet of the soil profile, we'd hope that we would have applied enough gypsum to cause the displacement of the sodium off of these cation exchange sites. Once we get these sodium cations displaced off the exchange sites, now they are free cations out here in soil solution. And I'm showing arrows here basically because in order to reclaim this alkali soil, we are far more effective if we can leach that soil profile, meaning applying water beyond the water holding capacity of the soil, causing these free ions that are no longer bound to the exchange sites to be capable of being moved down in that soil profile to some depth. The more water we can apply, the higher the amount of gypsum we put on, the more efficient we are in this exchange reaction, and the more efficient we are on leaching this sodium down below the root zone of the crop. Plants, or especially annual plants that are needing to be established from seed, are most sensitive to these high pH soils, which oftentimes will also have a high salt content during the early germination, seedling, and establishment period. So if we can create this condition where we've modified the pH of the soil and or leached out the excess sodium, even for a temporary, or not a long-lasting effect, but even a temporary effect, we can then get this crop established, which will be the most sensitive stage of development for that crop in terms of its sensitivity to either the high pH, the high sodium, and or the high salt content in the soil. Most often, the high content of sodium that exists in the soil and is on the exchange site is due to the presence of either the sodium carbonates or the sodium bicarbonate types of salt, which also contribute to high pH in soils. So this is general chemistry of reclaiming an alkaline soil by applying the amendment gypsum to the soil. Soil samples can be taken, sent into a soils testing laboratory, and the actual gypsum requirement can be determined. So you can get a quantitative determination of the amount of gypsum that it is going to require to bring the pH of that soil down into the desirable range and or displace the sodium and for calcium, and then be able to leach that from the soil profile. Now the question is often asked, if I don't have irrigation water and I have an alkaline soil, one that's high in sodium content, does it do me any good to apply the gypsum? And my response to that question would be that yes, indeed, gypsum will help just due to natural precipitation and rainfall and a certain amount of exchange that takes place in the soil. Because oftentimes when we have extra sodium in the soil, it actually becomes antagonistic to the uptake and utilization of the calcium, which of course is an essential plant nutrient, whereas sodium is not. So even if we can't leach the excess sodium down in the profile, the application of the gypsum at least applies additional calcium in soluble form that can help combat or somewhat offset the effect of the high sodium content in the soil. What we're going to be discussing next is what happens if we're on the other end of the spectrum. What happens if we have a soil which has too low of a pH or is too acidic? What material or materials can be utilized to reclaim that soil, and what process is involved in the reclamation of these acidic soils.